Okay. Today I'm going to continue on the introduction of CFD. Okay. So, but the focus of today is actually what is the general process, how to do the CFD simulation in computer. Okay. Last time I gave you a introduction on what is CFD and what's the history of it. Okay. Some background information, right? Today, let's look at a little bit more details on how, okay, how to do CFD. I think, let me share my screen, okay. I think a couple of video last time I couldn't show, right? I think let's play it. I can separately play it. Okay, let's see. Okay, this is the particle video, okay. Everybody see it? See the screen, right? Let me hit the stop button. Okay, so that's a particle injection, okay, from a inlet port of a room, a chamber. Okay, actually we did some experiment on measuring the particle too on the same size of chamber. So Fluent can calculate the trajectory of so many particles. This is just for illustration. It didn't show every particles. Okay, just so probably 1,000 particles here, but actually when we do simulation, you can put it. I think you can put as many as millions of particles. Okay, you probably couldn't put like a billion, trillion particles like a reality. You know, you have how many particles you don't know, millions of, right? So at least it's become better because now the computational power, computer power become more advanced. You have plenty of CPU, the speed is so fast, you have plenty of memory. Okay, so to calculate the trajectory of each individual particles. Okay, so the background flow field, it doesn't show. Okay, it's just showing the particle motion, right, and particle trajectory. But actually there's a background flow, as you know. You know fluid mechanics, right? It's a background that the flow carry the particle flowing away from each other and flowing to every different places in the chamber. And the end particle has its own motion, such as Brownian motion, settling, deposition, those kind of things. So it will interact each other, also have particle-particle collision or those interactions. So it's a very, very complicated problem. Think about it. It's really have no hope, no chance to do any study like this without a computer or without the CFD. Okay, experimentally, think about how to measure it. It's it's pretty difficult. Okay, even you have a sensor to collect particles. That's what we did. You can only collect particle on certain locations. There's no way you can actually see the entire picture of how the particle goes, what the trajectories. Here we can, right? You can narrow down to one individual particle if you want to really interested to see the trajectory. You can hide all the other particles, pick one, and see what exactly the trajectory it is, right? So it will be interesting to see. Okay, that's showing you what CFD can do, what Fluent can do, that software you are going to use. Okay. Okay, let's continue on the slides. Okay, let me turn on the waiting room. Seems like there's somebody in there. Okay, start from next week. Okay, we will have, not next week, the week after the week after the break, you have actually start the project. Okay. One thing I want to emphasize here is, please come to the class on time. Okay, it's very important to don't be late. Okay, it's not like other classes, you know, you can come in a couple of minutes late, it doesn't matter. Here, many of the class we do the project, okay, I will give instructions at the beginning of the class. Okay, I will leave time for you to do the project in class. I will have my TA to help. However, all the instructions, okay, a lot of the instructions and some discussion, I will, of course, do it at the beginning of the class. So if you come 5 minutes late, you might miss a lot of important informations. Okay, so
sorry, Dr. Fang.
Oh, no, it's all right. I'm not talking about you. Today is okay. Okay, so I guess start from next time. Okay, when we really start the project, I actually had a lot of say when every class, because there's a lot of instruction to give it to, especially at the beginning. It's kind of complicated. Okay, so please be on time. Okay.
Hey, Dr. Zhang,
Yeah.
will you be posting these PowerPoints onto Moodle so we can review them again and keep looking over them?
Sure, no problem. But those embedded video won't be able to show. Okay, so
yeah, I'm talking about the PowerPoints itself.
PowerPoint, not a problem. Okay, so also the class video also will be posted. I already posted the Mondays, right? Did you see it? Yeah.
Yeah, I did.
Okay, yeah. So, okay, now last time we are here, right? Okay, now let's talk about, let me put my display mode. Okay, yeah. What is fluid dynamics? I think we stopped at this page, right? So, it is a science of predicting not only fluid flow. Actually, it's actually heat transfer also included, right? It's a fluid dynamics. Heat is kind of like a flow. Okay, so heat flow, right? You have heat flow lab. So it's also we can also simulate the heat transfer, mass transfer, chemical reaction, and the related phenomena by solving mathematical equations. Okay, so the key is actually we're solving a bunch of mathematical equations. Actually, the differential equations, governing equations, govern these processes. Okay, and but how do we solve those equations? Not actually analytically. No, we're not doing that. Okay, so most of the equation is unsolvable. So we use approximation. Okay, so we break down the domain into small elements. On each element, well, supposedly the governing equation should be satisfied on each element. Okay, and it's supposed to be satisfied on each element, but we can't solve the differential equation, right? So we have to approximate the differential equation, change the equation into linear algebraic equation. Okay, it's an approximation. It's not true. Okay, it's not exact solutions. It's approximation. It's close, but not exact. So, but hey, we're engineers, right? We'd rather have some solutions better than no solution. That's the philosophy. Okay, for engineering purposes, you need to produce, right? You need to make stuff. You have to have something, to guide you. So even it's not perfect exact solution, we take it. Okay, it's better than no solution. Okay, in certain stance, it's pretty accurate, pretty close to the accurate to the exact solution if we do it right. Okay, so that's the process. So CFD analysis is relevant to engineering data. Concept just study it, or this is the purpose, right? So it kind of helps the design process. Okay, and reduce the total effort from the lab. See, I said a couple of times, actually you're doing numerical experiment in the lab, in the computer. Okay, so you can treat this CFD as a experiment, but you don't have to have a facility to do the experiment. Okay, you just need a computer. How great is that, right? So that's okay. Next slide is important. Okay, these are the equations. Okay, you are going to solve, at least attempt to solve using CFD. Okay, so I listed 5 equations here. Okay, that's probably all the equations you needed for most of the CFD applications. Okay, continuity equation. If you remember, we mentioned this in the fluids class, right? It's conservation of mass. Okay, so this is the differential form. Yes. Any questions? Anybody? I heard somebody talking. Okay. So this is the differential form. Basically, what it means if you divide your physical domain into the infinitely small element. Okay, on each of the element, these relationship will satisfy conservation mass and the three equations for the conservation of momentum. So momentum is a vector, right? You have 3 dimensions. So, and also the conservation of energy. Okay, look at them. These differential, they are all related. For example, energy equation, you can have, actually you have E as energy, but the velocity also included, right? Because that's a convection, right? And also diffusion. Reynolds number is even included, the Prandtl number, right? But for the conservation mass and momentum, you have velocity, density, velocity, pressure, shear, right? Shear is actually, you can construct it using velocity gradient, okay, velocity derivative. So that should be fine. So everything is velocity, UVW, and the pressure P, okay, for the incompressible fluid. Then energy, then you will have a temperature in place for the energy form, okay? So these are usually the 5 unknowns you can solve use these equations. It's called Navier-Stokes equation, right? That's famous one, right? Navier-Stokes equation. You know, in the new millennium, if you can solve the Navier-Stokes equation, you probably get a couple $1 million for award. They have their foundation for about 10 equations. If you can solve, you get a couple $1 million each. So, but I'm telling you, don't even try. There's no hope. Okay, partial differential equation. Look at this, 3-dimensional, unsteady. Okay, partial term here, unsteady, right? 3-dimensional, and also nonlinear. Look at velocity terms, uv, uw. Okay, these unknowns are together in the derivative, so it's nonlinear. Okay, so no way you can solve this analytically. So the only handful of the practical problem you can solve using this equation is under heavy assumptions. If you have a lot of assumptions, then you can remove many of the term here. So it become more simple form of the differential equation so that you can solve it. But it's very, very limited. Handful of the problem can be solved. For example, Bernoulli equation. Bernoulli equation is a solution from these Navier-Stokes equations. Okay, Bernoulli equations under heavy assumptions, inviscid, okay, steady state, right? Kind of 1D, okay, and irrotational, okay. So kind of a lot of assumptions before you can actually solve the equation, okay. So, but this is the general introduction. What actually is the equation? What animals you are dealing with? Okay, you are using those equations, directly solving those equations numerically. Okay, so, and our project, I think the first project will be a conduction heat transfer problem. So, energy equation is only equation you needed, right, for that problem. And then the second project, you will have all the, all the 5 equations involved, okay, for solving. Okay, so, okay, how does it work? Okay, so give you an example. So this is it's look like a tank with a nozzle injected. It's an injection flow in there. Okay, seems like a tank or maybe a reactor or whatever. It's like a tank in one of the car components, right? So what you simulate is the flow inside of this tank. Okay, so you try to calculate using those equations in the previous slides. Calculate the flow field and the temperature field inside this tank. Okay, again, I always mention the flow field and the temperature field, the word field. You're not calculating a temperature or a velocity. No, it's a field. Okay, that's your outcome. That's your product eventually. Okay, that's your deliverables, right? If you have a project, you have deliverables. So this is the outcome. It's a field of velocity, pressure, temperatures. Okay, so the field is actually the tank. Okay, so the first step is you have to generate this geometry, okay, in computer. Okay, you are simulating on a space, right? So you have to draw. So that required your knowledge, previous knowledge from which class? 演家 101, right? You need a drawing, okay? You know how to draw in computer, okay? So after you draw it, okay, this shows you the next step, very important, is to place mesh or grid, okay, on the volume that you're interested, okay, on the space that you're interested, which in this problem is the tank, okay, also a little bit pipe here or nozzle here, okay, when the flow getting injected into the tank, all right? So place your mesh. This is the confusing and the real-time problems, okay? A lot of people say, hey, I'm simulating a flow over a house, for example. They're trying to make the house, you know, in AutoCAD or in Workbench of the software. Okay, and they made a house, then they place the mesh inside the house. Then that's wrong. It's opposite to this problem. If you have try to simulate the flow over the house, a hurricane wind blow over the house, your volume of interest is the area, the volume around the house, outside the house. So if that's your volume of interest, you place your mesh outside the house, in the volume outside the house, not inside the house. You don't care about what's the flow inside the house. If you have a flow inside the house, your house is gone. So you're interested in the flow outside the house, right? So, but for this problem on your screen, your interested domain is inside the tank. So you put your mesh, okay? The software is able to automatically generate mesh for you after you give some inputs. For example, what's the size of the mesh, okay? What's the air volume you want to put the mesh on, those informations. It will produce some mesh for you, okay? But you need to be sure which volume you're trying to study, okay? Then to place the mesh on. Does that make sense to everybody? Okay. So what the computer do then, after you do the mesh, you import the mesh, of course, along with the geometry, into the Fluent package. Okay, think about it. You have an overall package called ANSYS. Actually, it's called ANSYS Workbench. Under the Workbench, it's an overall package Workbench. Under the Workbench, you have the geometry modular. You have the mesh generation modular. And you have the Fluent module, which is the actual calculation module. Okay, so after you finish the mesh, okay, then import it into the simulation package, which is called Fluent. Okay, then Fluent then you still need to set it up, put the boundary conditions, set the model, pick the correct informations. Okay, then and also select setups like a steady state simulation, unsteady simulation. What is the time step? Okay, those kind of things. Then you hit the button, Fluent will start to run. Okay, it will start to run as you instructed. What kind of equation you wanted to solve. Okay, so after Fluent done the simulation, it could take seconds, could take minutes, could take like weeks for one run. You know, I had a run when I was a student. I had sending a run before the winter break. After the winter break, I come back 1 month later, it just finished running. Okay, it's possible to run a long time, but I don't think in this class you will experience such a complicated case. So usually it would take, minutes or even hours to run. Okay, that's possible. So after the run, actually what Fluent do is it calculate the values, for example, velocity, pressure, temperature, on every grid point. Okay, you see the grid intersection. This is called grid point. Okay, so it won't calculate anything in between grid point. You see that the cells, right? These grid cells, but actually what computer do is it only calculate on the corners of each grid cell. Does that make sense? It only calculate, okay, values on those corners of each grid cells. Okay, so so then you know, okay, the finer your mesh is, the more data you will get. Okay, that makes sense. The finer it goes, more data, the more final the resolution data you will have. Okay, so that's one good thing about using the fine mesh, but there's a bad thing about using fine mesh too. Okay, I will talk about it later. So that's how it works. So you have thousands of data points. Okay, now you already see the advantage of doing CFD comparing to experimental measurement. If you have any chance to place the sensor inside this tank, you can measure a velocity or pressure or temperature on one location only in the real experiment. Is that right? You see the difference? Okay, now you have, after the simulation, after the run, you have thousands of data points inside the tank. Okay, you have very, very detailed information. And it's really difficult to, using physical experiment to have a comparable result. You know, you want to put 1,000 sensor in this tank, you know. If you can, you put 1,000 sensor in this tank, the flow field is totally different because your presence of those sensors alters the flow already. So what you measure is not reality, right? Okay, so think about that. You know, doing measurement, probably you're gonna get a couple points. Actually, in your car, they have sensors in those places. They have a couple sensors in the tank or whatever. If something wrong, it will show error message. All right. So okay. So that's how the process is, how it works. It calculates the values on those grid points. Okay. So those equations, okay, so between every adjacent grid points, the relationship between the values, for example, relationship between the velocities between two adjacent points should satisfy the governing equation here. Okay. If you can analytically solve it, you can also solve every locations inside a space, okay? So between every adjacent point, these 5 equations should satisfy between these 2 points. They have a relations, but it's too complicated, that relationship right now, right? So what we do is we simplify this into linear algebraic equation, make it linear equation. These equations are not linear. So look at the equation, the terms. From the second term, for the momentum equation, for example, second term, third term, or fourth term, these are the 3 nonlinear terms. Okay, so that tells you the shape is not a straight line between 2 points. Okay, nonlinear. Okay, so but we can solve nonlinear equations. Okay, so algebraic equation you're using like a matrix, you know. So we have to break it down and then transform it into linear equation. Assume the 2 point between these 2 points, a straight line, for example. Okay, so just like a calculus, you do integration. Okay, you assume those, you divide, you do integration, you know, to calculate the area below in curve, for example, right? You divide the area beneath the curve into rectangles. Rectangles are linear, right? The area is easy to obtain. They'll add them up. Okay, consider this is the overall area of the area under that curve. But you know, it's not true. Actually, it's approximation too. Until your spacing, every other spacing, delta x become infinitely small, then your area is infinitely close to the exact area. Is that right? That's exactly the same idea applied to CFD. So you have the finite spacing grades. Okay, you know it's not the same, okay, when doing the approximation. However, if the grid size is infinitely small, if the grid size is infinitely small, okay, the solution could be infinitely close to the exact solution. Okay, that makes sense, everybody? Okay, you see, when the computer become more powerful recently, there's a bunch of people in the research community, CFD research community, openly say CFD is actually an exact solution. Okay, they openly say this because they feel in the near future, the computational power will become so advanced and you can really divide the domain, divide the grid into very, 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 very small, infinitely small. You can have trillions of elements there. Okay, so actually, that's infinitely close to the analytical solution. Seems like we can treat CFD solution as analytical solution, even if you do it right. Okay, so that's my introduction here. So it is fundamentally is an approximation. Okay, but if its grid size is small enough, that approximation become more close to the reality. Okay, so now we're not there yet, right? So we'll have to have finite grid size. For example, your student license Fluent only allow you to have maximum 500,000 grids in a project, in a run. Okay, so 500,000 is your 500,000 is your limit. Okay, you can put infinite amount, okay, a lot of amount. So, but for our class, for the past project, probably you don't even need 500,000. Maybe tens of thousands is the maximum probably you need. Okay. Okay, so after you calculate everything, all the values on those grid points, okay, next task for the software is to post-process the data and show you some result. That's also a very, very important task for CFD engineers. Okay, so those digital data, you have a bunch of thousands of digital data every time step, even. So, it's too much, to handle. If you show those data to your client, nobody knows what that means, right? So it's a huge task to convert those data into digital images, into actually animations, videos, okay, and also some plots, okay. So this is called post-process, okay. In the early time when we develop CFD code programs, we have to write our own programs, right, to do the simulation. And then we have to spend a lot of time to post-process those data. It's kind of a task, very complicated, tedious task too. So Fluent has a post-processing package too inside the software. So actually, it just clicks some buttons. It will show different type of result, on different type of the visualization form. Okay, it can show the contours. That's one of the common ways to show. Use color contours. Okay, I think I showed you in the couple image before, right? Like the rocket, the airplanes. So, you have a color contours. You can select a 2D surface to let Fluent plot the contour values with colors. Okay, so higher value may be red, but lower value is blue. So it shows the distribution of those values on the selected surfaces. Okay, so but contour, you need to select a surface. It can only show on a 2D surface. Okay, you can show in the space contour, right? You can also show vector field. Okay, so I think I showed you one flow over the cylinder, right? Early, it's too slow. This one, right? Vector, it will automatically generate the vector field for you, okay, for you to show. If you select the vector display output, it will show you those errors, okay, on every grid point. Now you know, in the space around the cylinder, they have grids, they have mesh grids. many grids. So on each grid point, it will calculate a velocity for you, a velocity vector for you, okay? Magnitude and the direction. So you can plot it actually, okay? I'll plot it on every grid point. That's why there's so many arrows here, because every grid point, they plot the vector arrow, okay? But some point has nothing, right? Because it's so small, you cannot see, okay? Yeah. So, okay, that's some way to display the color. Also, you can place the color on the vector, so it shows the magnitude of your velocity, right? So, but you can separately contour it also. Okay, so these are the contours vector. What else you can use? Okay, I think you can use data plots. It also has the capability. You have all the functions that Excel can do, Fluent can do, many of them. Okay, so you can have XY plots. For example, you want to show a time history of that velocity on certain location. So you can pick a location, okay, as if you have the sensor in that location. Okay, you can let the Fluent plot the change of this value on that location versus time. XY plot. X could be the time, Y could be the value. So it will show the change of the value in terms of time. Okay, XY plot is also available in Fluent. Also, you can plot the profile. So if you just want to look at the instantaneous information, for example, from the bottom to the top in this tank, in the center, vertical center line, how the velocity changes. Okay, you can pick that line. Okay, you actually need to create a line to do output. Okay, it picks that line, it will output the XY plot. Okay, one is the location, one is the value, so XY plot, right? It tells you the change of that value along vertical direction. Okay, so there are many output visualization methods available in Fluent. Okay, we can explore some, okay, in the 2-3 project we're going to do. Okay, so that's the whole process, how it works. Okay, that's basically 4 parts: creating geometry, creating mesh, putting the Fluent to run the simulation, then post-process to analyze the data. Okay, eventually the analysis of the data is really important, because that's the interface between you as a CFD engineer to the client, which has no idea what CFD is. Okay, so you have to create a good outputs. Okay. Some word I want you to learn. Okay, so the most important word in CFD world is something called discretization. Okay, if you type in Microsoft Word this word, it doesn't recognize this word. It put a red line below it. Basically, that's a new word created by CFD industry. Okay, actually this means you transform the equation, the original differential equation, into algebraic linear equation set, which is called matrix. You're solving, the computer is solving the matrix. Okay. Did you guys remember that old movie, 90s Matrix? I have a series of the Matrix movie, 1, 2, 3, right? Hey, the world can be solved on a matrix. That's true, actually.
They're making the 4th one.
They're making the 4th one? Really? Seriously? They still have audience want to watch that movie? Okay. That's interesting to know. So you are solving a matrix actually in Fluent, okay, for the space you're interested. Okay, so discretization basically is the word that transform the initial equation into linear equation that the computer can solve. Okay, but how? Basically, yeah, it's easier to say than done, right? It's with an approximation, right? We change the equation, but there are many different ways to convert that equation into some linear forms. Okay, even different ways, they call it a model. Okay, a CFD model basically is so the linear equations eventually developed by some scheme, by some algorithm based on the initial equation. Okay. 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 A sticky point here is mesh. Okay, so I said it a bit before, you need to generate the mesh. Well, nowadays Fluent can automatically generate for you, but still when we do it, sometimes the way the automation by Fluent is by the ANSYS Workbench is not perfect, not preferable. Okay, so sometimes you still need to manually change on the some part of the mesh. Okay, but I'll give you an introduction of the mesh. So in order to cover a space of interest, your space of interest might not be simple. Okay, might be complicated shape. Okay, so you can use a single rectangular mesh to cover all the space, right? So because of the complicated shape, you have to have a complicated shape of different grades, like a triangle grade, tetrahedron, all kind of different shapes in order to body fit cover the entire space. Okay, so the numerical method, the models have to align with those grid mesh shapes. So based on the shape of the mesh, the equation has to change a little bit to take into account the shapes. Okay, so that's the process. So that's why the early time when we don't have those software, when we develop our own code, then sometimes we really need to be careful. We have to actually play with all those shape of mesh grades to make a good one. Okay, so it's not easy. Okay, and now Fluent do it for you, ANSYS Workbench do it for you, but still, sometimes it come out a bad mesh. It's really possible. Okay. The rule of thumb is the mesh has to be finer. I'm showing you this couple image here. Okay, I showed it's not entire mesh. Okay, for example, this airplane, it's a fighter jet, right? By chance know what kind of fighter jet it is? F-16. It's definitely not 22, right? Not 35. Okay, but whatever fighter jet it is, you want to simulate the aerodynamics of around the fighter jet, right? So your space volume of interest is air around the fighter jet. Okay, so you have to place the mesh to cover the entire space. Okay, of course, after you cover the entire space, you cannot see it's too massive, it's one block each other, right? So we choose a center cutting plane just for display purpose to see what the mesh looks like near the airplane. Okay, so you notice, okay, so the mesh has finer resolutions near the airplane, and it has much coarser resolution far away from the airplane. You know why is that? So do you think the flow is more complicated near the airplane, or it's more complicated away from the airplane?
Away.
It would be more complicated away from the airplane?
No, more complicated near.
Yeah, I think it's more complicated. Remember those vortices I showed you in the previous ones? You see that vortex? Let me show you again. The fighter jet. I have a fighter jet image there. I have fighter jet photos, right? In the early slides. It's slow. I want to show it with, okay. Somewhere, I think there's a, oh, where's my fighter jet? Fighter jet image. Did I show you one, or maybe in other slides? Maybe it's not in this one. Okay, anyway, we can look at this rocket, for example. You see very small flow structures near the fin of the rocket, see? Okay, kind of like more complicated, but far away from it, it's just free flow, just airflow, right? So it's not that complicated. The complexity is caused due to the presence of the object. Okay, that's why in reality, when we create the mesh, you want to make sure the Fluent usually will do it automatically, but sometimes it make a mistake. Okay, it's not guaranteed. You know, the flow structure near the structure near the object is complicated. Incomplete means they have small flow structures. Okay, you have small circulations, small vortices. Okay, near the object. But think about it, if it's small, it's very small, tiny vortex, for example. Notice your calculation only happens on those grid points, on the corners of the cells. It's nothing happens inside the cell. Okay, so if your grid cell is even bigger than the vortex, the vortex could be inside your cell, but you totally missed it. You didn't calculate anything, right? Okay, so that's the reason your size of your grid has to be smaller than the flow structures you are going to study. Okay, the complicated flow structure is very small. Those eddy vortices are really small. Okay, near the plane. So if you place such a big grid, then you miss many of them. So that's why you need to have a smaller grid size. Okay, near the complicated flow regime. Okay, another one down here seems like just an airfoil. Okay, the grid around the airfoil is very, very fine. Okay, because you have very small eddies created near the surface. Okay, so it has to be really fine to resolve those small flow structures. Okay. Again, there are some other examples, you know, use different sizes of grid to simulate, to cover some space. Okay. Again, this is also a injection to the tank. It seems like it places very fine grid near the injection port. You know the injection port where the flow enters the tank, it's very turbulent over there, the entrance port. Okay, it's very turbulent and very complicated. That's why you need a finer mesh to cover the region inside. Okay, it just shows the surface mesh, but also reflect actually the mesh inside the volume is also small like that. Okay, so what is this? A dinosaur. That's one good thing about CFD. You can simulate something not real in reality. Okay, so whatever geometry you can generate. But I think this one also, it just illustrates the surface mesh of the dinosaur in the ground for you. But actually the actual mesh, the grid is in the space around this dinosaur. Okay, nothing inside the body of dinosaur. You don't need to simulate what's inside the body of dinosaur. There's no flow there. Okay, everything is outside. Okay, but for the illustration purpose, it shows you the surface. You know, think about it. You have all the space mesh there. You can't see anything there. Too crowded, right? So that's why people show like this. Okay. Okay. So the things you need to know. Okay. So for discretization. Okay. Now, when you start to play with the software Fluent, okay, after you imported the mesh into the Fluent, these are the steps you want to take. Okay, first is for the discretization, right? Select a model. Okay, model means different way of discretization. Okay, you convert the initial governing equation into. Actually, everybody have some idea, invention, you know, developed. Everybody can claim their discretization is better than the others. Okay, there's no final answer which one is better. Everybody can have a better method of serving for their own purposes for different applications. Okay, the problem is really complicated, and the approximation is there's no uniform way to approximate. It depends on each individual applications. Okay. Your thing in this class is not to learn how to discretize. Okay, that leave it to the graduate school. Okay, for undergraduate student like you, are trying to identify different discretization models and pick one that's more appropriate for a certain application. Okay, so that's the first task. You have to pick correct models. There's really a bunch of models, a lot of models in Fluent. That's why it's difficult to use. Okay, it's sometimes you have to really rely on the fluid mechanical knowledge and some CFD knowledge to make a pick. Okay, so pick the flow models, the turbulence models, those kind of things. Okay, then they define materials. Okay, for the space you want to simulate, what is the flow? Is airflow or water flow or ethylene, acetylene, or whatever flow material is? You have to define it to make sure, because each material have different properties. When you do the simulation, of course, the result will be different depending on the properties of the fluid, right? So it's very important to pick the material, right? And determine the operating conditions, okay? Does it run, are you simulating under Earth's gravity, or you simulating under the Mars gravity? Or you simulating the environment of Moon, okay? So set the good operating condition. It's very capable of doing many other situations. So it's up to you to specify. Okay, so operating conditions. Okay, what is the reference pressure? Where is your reference pressure? Questions like those, okay, you have to answer yourself before you can actually select those conditions. Okay, these are related to the discretization and the models. Okay, some more information needed for solving any differential equations. You need the boundary conditions. I assume everybody had the Cal 3 and the differential equation math 301, right? So in order to solve a ordinary differential equation, partial differential equation, you need the boundary conditions, okay? The order of derivative, if it's second order, then you have to have two boundary conditions, something like that. Here, similar, okay? So you have a 3D space you want to simulate. The entire boundaries enclose that 3D space. You need to specify the boundary conditions on every boundary. You can't miss anything. Okay, if you miss any boundary surface, it's a non-closure. That won't give you any solution. Won't be able to solve. Okay, keep in mind this. This is a critical step because all your value eventually is propagated from the boundary. On differential equation, is actually boundary dominated. So the equation is just tell you a relationship between every two locations, right? Okay, equation only tell you the relationship, but actual value is from the boundaries. Okay, so in that sense, that tells you if you specify a wrong boundary condition, this is a garbage in, garbage out there. Okay, so no matter how pretty the picture the Fluent will give you, it's garbage. Okay, that's why I always say this Fluent is very difficult to use. Okay, so it will be misleading to the clients, okay, because clients don't know. So you need to have a quality that to make sure that you're simulating, the result from your simulation is not garbage, okay? You have to specify those conditions correctly. Another one called initial condition. So if you study a unsteady case, you have a partial time derivative in the equation. So it changes with time. So if that's the case you want to do, you need to specify a initial condition, the starting time, what's the result, what the value is. Okay, without knowing the initial condition, you can do unsteady simulation, right? And many times the initial condition is critical, okay? So for example, your weather forecast. Weather forecast is a CFD, as I explained before, right? So it really depends on today's weather for you to predict tomorrow's weather. Okay, so that's the initial dominant problem. So without knowing correct initial condition sometimes is as critical as boundary conditions. This basically is the boundary condition in terms of time. Okay, so if you don't have those values, forget about the simulation because there's no hope to get the correct value at the end. Again, trash in, trash out. Okay. Okay, then if everything set it up right, then you click the running button, it will run for you. Okay, so after you run the simulation, then is the difficult part starts. Okay, it's not the end of the story. Actually, the beginning of the story is after you see the results. Okay, I want to emphasize here, it will always give you a result, but it's not like some other software. It will give you reliable results. Okay, it will give you some results just like trash in, trash out. It will give you trash, and then 90% of the time it gives you trash. Okay, so you have to determine if the result is reasonable, and you have to verify your result and validate the result with existing data, with with measurement data, with experiment, or with existing literature data, or with a theoretical calculation. Okay, you have to make sure your result is not just color picture. Okay, you have to make sure it's correct before you present it to your client. Okay, which in this class is me. I'm your client. Okay, so you have to make sure it's correct. Basically, I think certainly some level of verification is actually necessary for every project you run with CFD. Okay. What time is it? 11:52. I have a couple minutes. I have 5. Let's spend a couple minutes on the grid independence study, grid resolution and the independence study. It's very important. As I said earlier, your accuracy of your solution is dictated by the grid size. Okay, grid resolution. So coarser it goes, more inaccurate it is, right? If it's grid space is big, then between every 2 points it's not linear. Okay, you are using linear approximations. Basically, it's not true. Okay, so the finer it could get you more accurate solutions, but the finer it goes, it take longer the computer to run. Think about it. Every time step, the computer need to run the equation for every grid point. If you put 1 million grid point there, every time step, it will run 1 million calculations. Okay, so when unsteady simulation, you might run thousands of time steps, or maybe you run iterations to get it to converge solutions. So you have to run hundreds of thousands of iterations. So every iteration you need to run the calculation on every grid point. It's very costly, very expensive in terms of time. Okay, so you have to always find a perfect, balance between the accuracy and the runtime. Okay, so in that sense, you can, every time doing very, very fine resolution, you have to sacrifice a little bit of accuracy, okay, to meet the timeline. Okay, so, but how coarse is coarse enough? How fine is fine enough? I should say this. How fine? You don't want to be very, very fine resolution. Okay, but you have to have certain. You don't want to be very coarse either. So what is the point? What is the line there? The line is this. Okay, the assumption is this: if the resolution is fine, that means the solution is more close to the true solution. Then, if you refine the mesh again, become even finer. There's only one truth, right? Philosophically, right? There's only one truth. Okay, if you find solution, if the solution is close to truth, if you refine it again, it will be similar to the truth, because you already reached the truth. Okay, in other words, you can actually logically, you can compare your solution on this grid size comparing to the next level, final level. If they are equal, or if they are close, that means if you refine it anymore, the solution won't change, which means you already reached the true solution. Does that make sense? Does the logic stands? Okay, but in other words, if you can refine it, if the result doesn't change, which means, hey, that's useless to refine it anymore. You spend more time to run it, so what? You get the same result. So you don't need to run that fine. You don't need to run that fine resolution. Okay, does that make sense? For anybody doing CFD, you need to remember this. Okay, your grid size is, you determine the grid size. Okay, there's no almighty method to determine what grid size is. Every problem is different. Every problem you simulate is different. It requires final or coarser mesh for every problem. Okay, so the way you determine it is to compare your result from a certain grid resolution to the final grid resolution. If the two sets of results are similar or close and they can't tell the difference, that means the resolution you use is good enough. Okay, you don't need to waste your computational power to do it final. Okay. Does that make sense to everybody? You need to do this process in the first project. Okay, that's part of the first project, is to determine the grid size for a particular problem you are going to simulate. Okay. I didn't see much of feedback from you guys. Is that good? So far, so good? Is that clear to everybody?
Yes, sir.
Okay, good.
Yes,
Good.
sir.
Okay, good. Okay, now, accuracy, okay, post-process, view the result. Okay, here I forgot one thing, convergence. Convergence happens at when you do a steady state simulation. Okay, when you do a steady state, which means in your governing equation, the partial t term is 0. In undergraduate fluid mechanics, we always assume steady state, right? Remember, we always assume it doesn't change with time. In many cases, it doesn't change with time. That's true. Okay, so there's only one solution. Okay, for the flow field, there's only one solution. So your task is, if that's the case, that's a problem you are going to simulate. The task is just to find out the set of the solution for the field. Okay, it doesn't change with time. So if that's the case, when you run it, when you start the simulation, it need iterations, because the boundary condition won't immediately propagate it into the entire domain. It take iterations. I don't know if we had a fluid project. Some semester I give fluid project for pipe flow. Remember, we use Excel iteration to get the solution. Okay, some class I did, sometimes I didn't. Okay, similarly, from the initial guess, right? Your initial condition, basically initial guess, your boundary condition might not quickly propagate to the entire domain. It requires iterations. Okay, after you iterate many times, gradually the solution doesn't change anymore. So we call it converged. Okay, the solution converged. That means the solution doesn't change anymore after further iterations. Okay, so when you do steady state simulation in Fluent, it requires to have the iteration process. Okay, so the Fluent will stop the iteration until the convergence criteria is reached. Okay, so in that sense, you need to specify a convergence criteria. Otherwise, when the Fluent is going to stop, right? So usually we use relative error as the convergence criteria. We say, hey, if the relative error between this time and the previous time is less than, let's say, 10 to the negative 4. Oh, you know what relative error is, right? The current value minus the previous value divided by the previous value, that will be a relative error, right? Relative difference, okay? If the entire domain, every point, okay, the relative error comparing to the previous time in every point, okay? You have maybe thousands of points in your space. Then check every point. If all of the points, the relative error is smaller than a certain criteria you specify, then Fluent will stop the iteration. Okay, so that's something you need to specify. Okay, it's a convergence criteria. But for the unsteady simulation, remember, unsteady simulation, nothing converges. The solution changes from time to time. So in some cases, it's unsteady, right? So like a weather forecast, the weather pattern changes every time, every second. It won't be the same. So it's unsteady simulation. There's nothing to converge there. Okay, remember this. Convergence is only for the steady state simulation. Okay, for the unsteady run, basically you need to specify the time intervals. For example, I want to start the run from 8 o'clock. The next time I want to know is 8:01. 1 minute after 8, 8:02 then. So I will simulate unsteady. I can simulate an hour from 8 to 9, but the time interval will be 1 minute, for example. So every minute, the Fluent will simulate a result, calculate a set of results for you. That result represent the result at that time. Okay, so it will propagate 60 times. Okay, if you put time step as 1 second, then it will go 3,600 times for an hour period. Okay, so it will calculate at any moment what the flow looks like. Okay. So this is two types of the simulation you are going to do. You are going to do steady state and unsteady simulations in the two projects we are going to do. Okay.
Dr. Zhang, I have a question.
Yeah, go ahead, Michael.
I know it all depends on your computer, but is there a way to predetermine how long a simulation may take?
Oh, you have to try it. You try a couple of times, you don't know how long it will take for your grade. Usually, if you have a grade less than 1,000, usually it should be fast. Okay, but I think some of the second project, probably your grade is in the, I don't know, I don't remember, about 10,000 range. Okay, so it takes a little bit to run. But for the first project, it's just seconds. Okay, you will run very quick. So maybe maximum a minute when you run the first project. I think, yeah, first project is quick. It's 2D, that won't have too many grades. Okay, but after you work in the field for a long time, based on the number of the grade you put in there, you can have the educated guess how long it will run. You will know. Okay, so this is a kind of like experience. Okay. Post-process, I already talked about it. There's a lot of manpower, expensive, and the Fluent have. Oh, look at this. It's a post-process from the flow of a dinosaur, long extincted, right? Okay, so it seems like there's some error. I use vector to plot it, on the center cutting plane on the space. See, that's what I say. The flow is around the dinosaur. No matter how the dinosaur is, there's nothing inside the dinosaur, right? Inside this object. Okay, the color representing the value. I guess you have a higher velocity or something. Is the color velocity? I'm not sure. Something higher on top of the head, something higher between the two legs. I think that's reasonable. High velocity because it's squeezed in, right? So some sample result here. Okay, this is another visualization. Just like I mentioned earlier, I use contours, color contours. So color contour, you have to pick a surface, pick a plane. Okay, it can only show only 2D, right? 2D results. So you pick a plane, although you have the entire space you simulated for the dinosaur. You pick a center cutting plane, for example. Okay, so it plots velocity and magnitude as color. So higher velocity and magnitude, it shows the red color. Lower velocity is blue color. So it seems like it give you a velocity field, okay, on the center cutting plane around the dinosaur. You have a high velocity on the forehead, between the legs, and low velocity near the neck, okay, back of the neck. That seems like reasonable to me. Some surface information. As I mentioned earlier, surface data is important for the designer. You design a fighter jet, airplanes, you have to know the surface pressure. So this is the surface pressure field. on the entire dinosaur surface. If you change it to a car and change it to an airplane, so it show you the surface pressure distribution, which is very valuable information. If you don't have a computer, you have to place many sensors on the surface to get a clear picture what entire picture looks like. Okay, here it easily give you the entire picture. What's the pressure? High pressure around these areas. Okay, low pressure around these areas. Okay, so I give you a taste of what the result gonna look like. So when you process the data from your simulation, these are also the method, okay, you are going to use. Okay, not examine the result, examine the result. Okay, so test the result. You know, you have to not test the result, verify the result, basically. See if the result, the first layer of the examine is to ask yourself if the result is reasonable. You have to look at it's not, let's look at, hey, it's a color picture, I'm happy with it. No, this is just the beginning of your project. Okay, that's just the beginning of your task. First of all, look at the result, examine for the first time with your education background, with your experience. Is the pressure higher inside the mouth, like on the tongue of this dinosaur? Okay, from my background experience, I feel it is a high pressure point because the flow hitting it. It stopped there. Okay, flow is from the front to the dinosaur. So that's a stagnation point, basically. That's why it's at a high pressure on the nose. Obviously, this is the stagnation point. The flow stopped here. You have high pressure. So first examine is by your experience. Okay, is that reasonable? Okay, to me, this is reasonable. Okay, qualitatively reasonable. So good. Then go on to the next layer of verification. Can you compare some of the data? Maybe 1 or 2 points. You don't have a dinosaur to compare. Make a toy dinosaur, maybe put it in the wind tunnel, get some data. Okay, compare it. So then you will build a little bit of confidence in your result. Okay, don't trust your result. Again, I say again, many times during the semester, don't trust your result. Don't trust your result. Okay, verify it before you tell anybody. Okay, whatever you say, it has to be, you have to have a warrant, right, behind it. So don't trust anything from CFD before you actually verify it. You know, you don't have to verify every case. For example, you simulate many cases for the design you want to do. So maybe pick one, or you may pick one easier, and you have benchmark data or have something to compare to. Then if compare well, that means that for the similar simulation, like the one you compared, it should be fine. Okay, not exactly same, but maybe similar should be fine. Then at least you will have a little confidence, okay, in your work. Okay, I guess that's probably it. This is I'm afraid I hit the button, it will crash my. Okay, is that running? Okay, this is the heat transfer problem because you're gonna do a heat transfer for the first project. This is the heat transfer. This is the circular under ocean pipe. Okay, under ocean pipe. It's a heated pipe. Okay, so it fluctuates a little bit. You notice I crashed my computer. Okay, so it's all right. I can turn on separately with the video if I can find that video. Okay, I think this is the one. I will share my screen in a second. Give me 1 second. Let me turn on the video. Okay, let me stop it here. Let me share my video. Now you can see it, I guess. Okay, let me play it. Now you can see it, right? Can you? See, the pipe oscillates a little bit under ocean wave, right? It oscillates. And it shows you the heated pipe generated from the surface of the pipe, how the heat is transferred in the ocean water. The flow is from left to the right. Okay, you have an ocean current. Okay, so that's how actually the heat transfer follow the vortex shedding, follow the flow. This is basically the flow pattern, but also it's a heat transfer pattern. It's a temperature, right? Temperature, see the heat is move away. It's not from any direction. It's actually through the wake behind the pipe, okay? By the vortex is shaded like this. Actually, the vortex is carry the heat away. Okay, very important. Some people designing the heat exchanger surface like that. I have a capstone project actually to design heat exchanger surface. How the convection heat transfer, right? How do you effectively transfer heat? Actually, a lot of them is from the turbulence. You have a vortex, eddies generated from the surface. If you have a lot of vortices, actually when it move away from the surface, it will carry the heat away. That's actually one of the dominant mechanism of heat transfer. Okay, is a vortex shedding. So that shows that this video actually proved it. Actually, your temperature, see the high temperature actually transferred basically totally follow the vortex. Okay, I think that's a good video to show. Okay, let me. I think I'm at the end of the slides. I think I'm at the end of the slide. That's about it for what I tried to talk about. I think there's one more slide here to show the limitation. Okay, let me share that. That's the limitation of the CFD. I think I already mentioned. I asked you to do not trust your result. Trash in, trash out. That's the limitation. Okay, that's always the attitude you need to have towards CFD. Okay. Did you see that? Just one slide here. Limitation of CFD. Could you see it?
No.
No? Okay. Okay. Share again. Every time I run video on my PowerPoint, it crashed it. Low system resource may affect your quality. Yeah, I know, low system. Okay, it doesn't matter. It's just a limitation. I think that a lot of errors could possible. Okay, we don't need the screen. I think many errors are possible. So first error is from the truncation. Discretization. Right? When you change the equation, you totally change the equation. It's not the equation actually, analytical equation. It's become a matrix. So that process gives you errors. Okay, you have to control the grid size to minimize the error. Then you have error from the numeric model. You cannot, we use we basically use the Taylor series, Taylor expansion to discretize the equation. Okay, so Taylor expansion have infinite number of terms. Can you still hear me? So it have a lot of error when you truncate the terms. If you have infinite number of terms, you can't put it in the computer. You have to just keep a couple terms there. So that gives you error, okay? And then the boundary condition, initial conditions you place there give you error. It's not exactly reflecting reality. So many source of errors. So many source of errors. So when you do iteration, it will propagate. Okay, when you don't do a time simulation, it will also propagate it with time. So that's why I always say trash in, trash out. Eventually, you have to make sure the result is reasonable. Okay, so a lot of errors could be. You have to know how to control the errors. Okay, then have some useful information eventually at the end. Okay. Okay, I guess that's it for my talk today. Did you guys hear what the last portion, what I talk about the limitation?
Yes, sir.
Yes,
Okay.
sir.
Okay, great.
Yes,
great.
sir.
It shows some audio errors on my screen. So, okay, I guess that's it for today. I guess I'm done. And then Monday after the break, we will, please make sure your ANSYS works on your computer. Then we will start some tutorial and on how to run it, okay, on the computer. Okay, so have fun. Have a good spring break. Be safe.
Have a good day.
You too.
Gracias.
You too.